You're listening to the Effective Statistician Podcast, a weekly podcast with Alexander Schacht and Benjamin Piske designed to help you reach your potential, lead great science, and serve patients while having a great work-life balance. Today we talk about linear mixed models. Okay, maybe if you're an experienced statistician, you think like, well, that's a pretty trivial thing. But I know that there's lots of misconceptions around there, and maybe a nice refresher is good. And if you are listening to this as a data scientist, as a programmer, I highly recommend this to you because you'll gain some additional insights or also just a refresher. So stay tuned for this discussion with Paolo. We are adding more and more trainings around R to the Effective Statistician Academy. So check out all the different trainings on the Academy. And if you are someone who would like to also contribute content to the Academy, then just reach out to me at alexander@theeffectivestatistician.com. I'm producing this podcast in association with PSI, a community dedicated to leading and promoting the use of statistics within the healthcare industry for the benefit of patients. Join PSI today to further develop your statistical capabilities with access to the video-on-demand content library, free registration to all PSI webinars, and much, much more. If you haven't yet registered, I will highly recommend you to register for the upcoming PSI conference in Amsterdam. Just head over to psiweb.org to learn more about this and all the other PSI activities. Welcome to a new episode, and this is again with Paolo. Paolo, how are you doing?
I'm very good, Alexander. How are you doing?
Very good. It is actually the second episode that we record today, but you, of course, don't know about these things because you get these episodes in a different way. And of course, we record all these episodes quite ahead before we publish them. Today, we want to talk about linear mixed models. And this will be the first episode in a series of episodes where we talk about linear models. So let's start first a little bit with why actually linear models in the first place? So when have you first get in touch with linear models?
I think linear model in general, as of the inclusion of random effects model, started when I was, at the university for my first degree, because it's kind of a standard approach for the first experience with a model. Because it's simple, is nice, is insightful, and you can learn a lot and then build on this specific model and expand the tool to incorporate the features of the data.
Yeah. And now, when we talk about linear models, the important thing to have in mind, it is linear in the coefficients that we talk about. Yeah. So linear in a sense that there's the dependent variable y equals to beta times x, and x being the independent variable or variables, and it's linear in the beta. Yeah, so that is important to understand. It has nothing to do whether the axes are linear. They can be, you can have quadratic terms in there, or logarithmic terms, or interactions, or all kind of different things. The important thing, it is linear in the beta. Yeah.
Yep.
That's just a little bit of a background. Very often people think like, oh, but that curve is obviously not a line. That has nothing to do with being.
Yeah, of course.
Yeah. So you can have y equals beta 1x plus beta 2x squared to be logarithmic of x. Yeah. This is still a linear model because it's linear in the beta 1, 2, and 3. Yeah.
Yeah, of course.
So just a little bit of a sidestep to that. Okay, so a little bit of history. Where are these models coming from?
So when we speak about linear mixed effects model, I think that everything started in the early 80s. We the paper in the 82 from the well-known Lerner Rubin.
Yeah, okay.
And then there have been few improvements, and then everything started to grow with more refinement, fine-tuning, more expansions on the tool, and we have a lot of tool that specific area.
Yeah.
So I think that it's quite important to note that still, we are using these methods from about 40 years, but they seem relatively new to a lot of people, and probably also we have a lot of people using them without knowing all the assumptions and the implications there, because there are quite a lot of intricacies.
Yeah. Yeah. So, and that's the first interesting thing that you talk about is this mixed models. So what I just talked about is y equals beta x. Yeah. That is the original model. And where basically plus epsilon is at the end always. Yeah. And that epsilon gets you the normal variability. Yeah. So you always condition on the x and you assume the x to be constant. And then the epsilon that is somehow distributed. Usually we just assume it to be normally distributed. And that is the error term. Yeah. Now, in reality, of course, the x is usually not completely fixed. Yeah. So the x can, of course, be things like a treatment group. Yeah. Then that is fixed and you can actually change it and things like that. But very often these can be other factors like baseline disease severity. And this is, of course, also something that comes with measurement error and all kind of other things. Yeah. So you condition on it, and by doing that, you take it as fixed. But that is also a big assumption that leads to all kind of different things. Yeah. So for example, if you measure something very imprecisely, that will have an impact on the beta and always push the beta closer to zero rather than away. The other thing is that, of course, there's assumptions about independence here. Yeah. So we usually assume that all the different patients are independent from each other. That is the first thing. Now we can lessen this assumption by having this mixed effect. Yeah. So we basically add another, I don't know, gamma times z or something like this, with the z being random variables. Yeah. And through that, we can then model, for example, that certain patients may come from, let's say, the same center and therefore have maybe, especially if you have these cluster randomized studies, they come, and have a covariability. They are not independent of each other. Yeah, and so there's a covariance matrix that is not just diagonal. Or you have repeated measures. Yeah, so that you have multiple measures and they all come from the same patient, and then you assume some kind of correlation structure there as well.
Yeah, for example, when you have repeated measurement, of course, the repeated measurement within each individuals are not independent. And you're not interested in learning for each and every patient how much these observations are related or the difference between these two observations. So instead of modeling this as a fixed term, we can think about random variability,
Yeah.
modeling the errors within patient, but of course without imposing a single effect per patient, but maybe thinking of more general random effect in which you have a single realization per patient, and you can effectively model the data respecting their nature and also estimating what's important for you, like the treatment effect or the effect of time.
Yeah. So these in this random effect, basically if you think about you have this beta x plus gamma z, the z's are normally distributed variables, and they all center around 0. So they don't add any main effects, but just add variability. And you're interested in understanding that. Now, you can have all kind of different assumptions about that. So, for example, you can assume like you don't know anything about the variability. And then you have these covariance metrics where you just assume them to be, covariance metrics in that sense. They are symmetrical and these kind of things. But basically, the degrees of freedom is here that, every cell has its own value and that there's no restriction on that. In other circumstances, of course, it could make sense to use different covariance metrics. So this in SAS, I think it's called unstructured covariance metrics.
The more flexible is the unstructured covariance metrics.
That is a maximum flexibility. But of course, you also need to estimate all these parameters. And estimating all these parameters leads to lesser degrees of freedom. And so more instability. If you have lots of patients, well, that's not so much of a problem. If you have less patients, then yes, that can become a problem. In these cases, you can also assume other covariance metrics.
Could be something more parsimonious, like assuming an autoregressive structure, for example, that you have the same covariance for the same lag if you're thinking about repeated measurement, or you can impose different constraints. For example, if you're using unequally spaced time points, you can assume that time points equally spaced have the same measure, and it's different if the space between time points is different.
Yeah. Another thing that you might have is this compound symmetry, where all the covariances are all the same, because you have this kind of symmetric approach. That, for example, could happen if you have certain kind of biologic experiments, and they all come from the same plate or something like this. So they all share the same background noise or something like this. So it's sometimes really helpful to have a look into these to understand, especially for smaller sample sizes, can I make that model more effective? By being more restricted and not adding too many degrees of freedom.
It depends on the sample size and also for repeated measurement models, for example, also on the number of the time points.
So if you run a phase 3 study with lots of patients, that's usually not so much of a problem. If you run a phase 1 study with very few patients, it can be something that is interesting to look into. So that is a little bit of the background around it. And we will, of course, put some show notes around this into the documents of the homepage. So just check out the corresponding homepage here of this episode, and you will find some additional details there. We'll also put some code there so that you can have a look into this as well. Okay, now that is all frequentist in a way. You think about that also from a Bayesian perspective?
Yes, in general, Bayesian models have been proposed to deal with these kind of structures, and also you can have also Bayesian flavor also when you do the standard frequency estimation, when you have the empirical Bayesian estimates after the standard maximum likelihood and the restricted maximum likelihood approach, because this is implicitly driven by the inclusion of the random terms
Yeah,
in the models.
yeah,
So
yeah,
it's a nice way of looking at this family of models.
yeah. Now is all kind of in the perfect world of when you're at university and you get these pristine, very clean data sets where all patients have all observations and you have no missing values and very, very clean data. Now, in real life, we never have that. We never
Yeah,
have completely clean data, but rather we have missing values or we have flawed values that we need to kind of consider, all these kind of different things. But missing values is really a big problem. Now, what do we do with missing values here?
I think that there is understanding. So you can often see that you have an estimation with mixed models and you have a complete case analysis discarding missing data. But this is not really the case because when you perform mixed model for longitudinal data, for example, and you have a mixed model for repeated measurements, then you have a model-based imputations, because
Mhm.
you, in a way, the software is estimating what happens, taking into account the hypothetical values you have from similar observations in the data. So
Yeah.
at the end, you have a model-based action. And of course, for example, speaking the estimate, terminology, speaking the estimate language, the only estimate you can align with this kind of analysis is the hypothetical strategy estimate.
Yeah.
It's not possible. You can use more sophisticated models, but with the standard one, you're able only to estimate what is aligned to an hypothetical estimate, because you are estimating something by imputing missing data with your model, relying on the missing at random assumption.
Yeah. And that is a very, very important thing to have in mind. If you run these standard MMRM approaches, and you can find code for that all around, yeah, you also impute in a way. Yeah, you impute just based on the model. Yeah, of course, you don't impute in the data set before in SAS or in the R data set before you run your MMRM. You do it in the model. And that's an assumption that you need to be aware about. Now, of course, what you can also do is impute all kind of other ways. Yeah. So a very frequently done thing is, for example, last observation carried forward. Yeah. So for everybody that drops out, you take the last value and impute all the other values that come afterwards with the last value. And that basically speaks to an estimate that assumes that as soon as you stop treatment, you retain the treatment effect thereafter. Yeah. Could be, in certain situations, a reasonable assumption to make. Yeah.
Yeah.
Now, of course, and that's maybe a little bit of a philosophical thing, is you actually add data. Yeah. And so that has an implication on the precisions that you do and all these kind of different things. And do you really add data, or is that, you add data because you have this assumption? That's maybe a little bit of a philosophical discussion, but be aware about that. Of course, you can also say, well, we assume that it stays the same, and we know that there will be always a little bit of variability. Yeah. So, and that's then where you can start to do certain things like multiple imputation. Yeah. So you have this last observation carried forward plus some kind of random thing around it. Yeah. And with multiple imputation, you basically create many, many different data sets that all look the same except for the values where you have imputed. Yeah. And there you impute them based on a distribution that you want to have them. Yeah. And as I said, in this very simple example with the last observation carried forward, you just use the last value, carry it forward, and add some kind of variability around it. So, for example, you know that kind of the between visit variability within a certain group, let's say the placebo group is X, yeah, and you use the same variability here so that you don't kind of add too much kind of stability to it just through the assumption. You can, of course, also think about other estimates. Yeah, you can think like we assume that everybody that stops treatment returns back to the baseline. Yeah, could be another. Yeah, that is sometimes called baseline observation carried forward. Yeah? Could be another thing. There you could do the same thing with the multiple imputation and things like this. The important is that you are very clear in terms of what you do, why you do it, and you explain it clearly in your publications and your communications. I've seen it again and again that people speak about, oh, this is the multiple imputation estimate. And I think like, what kind of multiple imputation have you used? You can think about all kind of different sorts of multiple imputation. That is not the multiple imputation. There are many multiple imputation things. Yeah.
You have to think to reasonable assumptions and figure out what are the potential realistic trajectories of your participants after they drop out and you have missing data.
Yeah, completely agree. So be aware about this. Now, that is all the theory. Yeah, there will be also a couple of references we will put into the show notes. Yeah, to check out about kind of fixed versus random effects and how that also relates to other modeling approaches like multi-level modeling, like hierarchical models and all these kind of different things. Yeah. So we'll put that into the show notes. And there's also the software corners that we want to shortly talk about. Paulo, what's the software corner for the episode today?
I think that for this kind of models, SAS is still the way to go. Although R is catching up, there are cool progresses like the MMRM package released very recently. But still, I think that SAS is the way to go. And there are also capabilities for simplifying a bit the estimation algorithms and working with big data set with the HP procedures from SAS.
Okay.
And many others. But to name the big players here, I think SAS and R are very interesting.
Awesome. Thanks so much. So check out the show notes. You'll find lots of additional helpful things there. And yeah, rethink how you're using all these different models and have a look into the different assumptions around your covariance structure, have a look into the different assumptions about your imputation methods, and think about these models as linear, even though the lines doesn't need to be linear. Yeah, so that's the last thing. I've seen that again and again being confused in the past. Thanks so much, Paulo, for recording another great episode. Have you already seen all the different courses that are available on the Effective Statistician Academy, just head over to the Effective Statistician homepage and check these out there. This show was created in association with PSI. Thanks to Rain and her team at VVS who helped with the show in the background, and thank you for listening. Reach your potential, lead great science, and serve patients. Just be an effective statistician.